Hi everyone. Our project mainly focuses on the electric power drill, one of the most widely used power tools in construction, woodworking, and mechanical assembly. What makes the drill an excellent case study is that it's not just one material or one process. It brings together metal cutting, polymer processing, heat treatment, and electronics all in a single handheld product. Our team analyzed six main components of a standard 18V cordless drill. I'm Doa, and I'll start by giving an overview of the product and its components. As you can see in this diagram, the six components we analyzed are the chuck, the motor, which includes the rotor and stator, the gearbox, the shaft and spindle, the housing and body, and finally the trigger and switch mechanism. Each component uses a different primary material and a different key manufacturing process. For example, the chuck uses tool steel with CNC turning and gear hobbing, while the housing uses glass fiber reinforced nylon produced by injection molding. This variety is exactly what makes the drill such a rich engineering case study. And here we see inside the drill. This photo shows the internal layout of an electric drill with the housing removed. You can clearly see the motor in the center with its copper windings, the gearbox connecting the motor to the chuck, and the trigger mechanism at the bottom of the handle. Each of these components has been carefully engineered, both in terms of material selection and manufacturing process. My teammates will now go through each component in detail, starting with the chuck.
Thank you, Doa. I'll cover the chuck and the motor. The chuck is the component that grips the drill bit. It must be extremely hard and wear resistant because it's subjected to repeated clamping forces and tool changes during its service life. The material selected is medium to high carbon steel, specifically C45 or IC1080, which achieves a hardness of 58 to 62 HRC after heat treatment. Chromium content in the alloy also provides corrosion resistance. In terms of manufacturing, the outer body, taper bore, and jaw slots are first formed on a CNC lathe during turning and boring. The jaw guide channels are then Prussian milled for smooth travel. The internal gear ring is produced by gear hobbing. After machining, the parts undergo carburizing and quenching for surface hardness, followed by final cylindrical grinding to achieve IT5 to IT6 dimensional tolerance with a surface roughness of RA 0.8. Finally, the jaws, sleeve, and body are assembled and function tested. Moving on the motor. The motor consists of two main subcomponents, the rotor and the stator. The rotor uses silicon steel, specifically grades M19 or M27 combined with copper windings. The shaft is made of IC1045 medium carbon steel. The stator uses laminated silicon steel sheets with enamel-coated copper wire wound around its slots. The key reason silicon steel is chosen is that it minimizes eddy current losses due to its iron silicon alloy composition of approximately 3% silicon. The copper windings are selected for their excellent electrical conductivity, and the enamel coating provides electrical insulation between turns. The manufacturing process begins with stamping and blanking, where silicon steel sheets are punched into the lamination profiles for both rotor and stator. These laminations are then stacked and bound to form the cores. Copper wire is wound around the stator slots using automated winding machines. Varnish impregnation follows for moisture resistance. The rotor shaft is turned on a CNC lathe with a kiwi milled for gear engagement. Finally, the lamination slag is pressed into the shaft and dynamic balancing is performed to eliminate vibration.
I'll now cover the gearbox and the shaft. The gearbox is actually a mechanical link between the high-speed motor and the low-speed, high-torque output spindle. It must be extremely durable under continuous cyclic loading. The gears are made from case-hardened alloy steel, which achieves a surface hardness of 58 to 62 HRC while maintaining a tough core. The gear teeth are actually lubricated with grease for extended service life. The housing is a die cast from ADC12 aluminum, choosing for its lightweight, good thermal conductivity, and ease of casting. The manufacturing process starts with gear hobbing, which the gear teeth are actually cut using a hobbing machine for spur and helical profiles, as you can see in the photo of the gear hobbing machine. This is followed by case carbonizing, which the gears are heated to approximately 920 degrees Celsius in a carbon-rich atmosphere and then quenched to achieve the required surface hardness. The tooth flanks are then ground to produce a precise involutes profile meeting AGMA quality standards. For the used housing, molten aluminum is injected into a steel die at high pressure. This is the die casting process shown in the photos. Bearing bores and bolt holes are then machined on a CNC machining center. Finally, gears, bearings, and shaft are assembled, backlash is set, and the housing is sealed. The shaft or spindle transmits the rotational torque from the gearbox to the chuck. It must withstand high torsional fatigue loads from repeated drilling operations. The material is AISE 4140 or 42 CR4 chromium molybdenum alloy steel, which achieves a tensile strength of 900 to 1100 MPa after heat treatment. The core hardness is 28 to 42 HRC, while the surface is induction hardened to 45-50 HRC for wear resistance at bearing contact points. The manufacturing starts with hot-rolled 42 CR MO4 bar stock. The CNC lathe rough turns the outer diameter, leaving approximately 0.5 mm of grinding stock. A center hole is drilled for machining support. Case slots are then milled for chuck and gear connections. The shaft undergoes quenched and temper heat treatment to reach the target mechanical properties. Cylindrical grinding brings the final outer diameter to H6 tolerance for precision bearing fits. Finally, splines are rolled, not cut, because rolling introduces compressive residential stress that significantly improve fatigue strength. As shown in the engineering drawing, the total spindle length is 110 millimeters with crucial features including the bearing set, keyway, and spline section.
I will cover the last two components and to wrap up. The housing needs to be lightweight, electrically insulating, and strong enough to survive the ropes and vibration. It's made from PA66 GF30, a glass fiber reinforced nylon, which can handle up to 150 degrees without deforming. Metal inserts are added at the screw location for extra strength, and the handle is overmolded with TPA rubber for comfortable grip. The whole shell is produced by injection molding using a two-shot process for rubber grip. The trigger body is molded from PA66 nylon, lightweight and electrically insulating. The electrical contacts are brass for low resistance, and the return spring is stainless steel for durability. A PWM controller integrated into the PCB allow variable speed control. The key manufacturing steps are injection molding for the body, stamping for the press contracts, spring coiling, and SMT soldering for electronics. To summarize, the electrical power drill brings together six very different manufacturing disciplines in single-handled tool. Metal cutting dominates the metal components. Heat treatment is critical for hardness and fatigue life. Die casting produces the aluminum gearbox housing, and injection molding gives us the lightweight insulting body. Even the electronics are integrated through PCB assembly. It's a great example of how modern manufacturing engineering combines so many fields into the one everyday products. Thank you.